Okay, let's go for the next topic. The next topic is gonna be linear momentum. Let's see how we can find the equation, how we can derive the equation that give us, right, the linear momentum. Imagine that we have an object, right, with mass m and with a velocity v1, and later the same object is with a graded velocity or speed, right? Imagine case 2, the same object but different velocity. Now, do they have the same amount of motion? Well, no, right? Because one is moving faster than the other one, meaning that motion depends on what? On the speed. Okay, now let's see the other case when mass is different and the velocity is the same. Okay, imagine this is m1, this is m2, m1 and m2, correct? Now they have the same velocity. Again, do they have the same amount or quantity of motion? Well, it looks like this one has more motion than this one, right? Because it has more mass, right? Now, when we combine these two quantities, velocity and mass, we create a very important quantity, right? And that is called momentum. And that's the symbol, right? Momentum is defined as mass times velocity, right? So that's the definition for momentum. Also, momentum is known as the quantity of motion, and depends on what? Depends on the mass, and depends on the velocity. Vector, momentum is a vector, right? So depends also on the direction. So we can work them with vectors, right? So in this case, the net or the sum of the momentum is equals to what? Momentum, right? Particle 1, this is for a system, right? Plus, right, momentum particle 2 plus and so on, equals to what? To mass times velocity, correct? Also, we can use the vector notation, right? For example, using component, right? The total momentum is equals to what? To a momentum, right, in the x direction, right? Plus, right, the total momentum in the y direction. See, so this is the vector notation for the momentum. Also, we can find, right, the magnitude, right, and the direction the same way as we did for any vector, right? So magnitude is equals to what? The magnitude equals to the square root, remember, right? This component square in the x direction plus the component, right, in the y direction square, right? Because again, momentum is a vector. Now we have a new quantity, where momentum is a new quantity, and it needs a unit, right? Now, what should be the unit? The units of momentum, well, depends on the units of the quantities. In this case, mass and velocity. So what should be the unit for momentum? Well, units of mass, kilograms, right? Units of velocity, meters per second. So that should be the unit of momentum. Okay, now let's involve force. Let's see how momentum is related to force. Okay, imagine that we are dealing with Newton's second law, which is defined the net force, right? Net force is equals to mass times acceleration, right? But how do we define acceleration? Well, remember, acceleration is just the change in velocity, right, respect to time. And also, well, the change, remember, is just final minus initial, that quantity, right? So we have, in this case, final velocity minus initial velocity, right, divided by the time, delta t. Okay, great. Now, let's substitute this value right here. And then what do we have? We have that the net force, just force, right, equals to what? Mass times, right, final velocity minus initial velocity, right, divided by time. Correct? When we multiplied these quantities, what do we have? Well, we have, and this becomes mass times final velocity minus mass times initial velocity, right? Divided by the time, right? Perfect. But what is this quantity? What is this quantity? Well, this is just momentum, linear momentum. Okay, so we can apply the definition right here, right? And what do we have then? We have the force is equals to, okay, net force equals to the change in momentum, right, with respect to time. So this is a very important quantity, right? So the force is the change in momentum, right, respect to time. Okay, great. Now we can have another arrangement, right, in this way. Because what is the topic? Momentum. Right now, let's solve for momentum. In this case, change in momentum. And what do we have? We have that the net force times this change delta time, change in time, right, equals to, right, change in momentum. Now again, every time, remember, we have a quantity multiplied by another quantity. We create a new quantity, we have to define it, we have to name it, call it. And we call this the impulse. This is called impulse. Impulse, right? Now, we need a symbol for impulse, right? One of the symbols is this one, right? J, right? Impulse is equals to, right, force, net force times the time elapsed, right? And also we can say this is equals to, right, change in momentum. Okay, great. So impulse also it has it's a new unit, right? A new quantity. So we need a new unit for impulse, right? So for impulse unit, gonna be the units of force is newtons, and the units of time is second, right? So units of impulse, newtons times second, units of momentum, meters, right? Kilograms, meters per second square. At the end, these two are the same, right? They have the same unit, but we differentiate these two quantities in this way. Okay, look, when we're dealing with the impulse, especially when we have collision, right? When we have impact, right? Collisions, and the time usually is very short time, right? When you hit a ball, right, with a bat, right? The time of contact is very short, so we have an impulse, right? We apply a force in a short time, a very short period of time, right? Okay, and that's gonna be to have an idea, the impulse. Correct. Now let's go to where we can work with impulse because we're dealing with collision, with impact, right? And when we have impact, well, we don't know exactly the force. We usually use the average force, right? Because we expect the collision to be kind of elastic, right? We have like a spring, we have compression, right, and expansion. So we can represent that impact, right? That impact or collision, right, in this way, right? With compression, right, and expansion in that way. If this is, right, force, and this is gonna be time. Usually when we have a quantity that changes, we use the average, okay? Imagine that we use the average right here. Imagine as the average could be, well, it will be below right here, right? Okay, that's the average. So this is the average force times the time we create, right, the impulse. Remember, every time we have a graph like this, we're looking for the area, right? Area under the curve, and the area is the product. In this case, force times time, but force times time is just the impulse. So we expect this area, right, to be the impulse. But again, we use the average instead of, right, this function. As long as we know the function, right, how it changes, right, this curve respect to time, we can use it. But usually we use the average, correct? So we can say, right, that the impulse is just this average force, right, times time. Also, we can use calculus, right, coming from from this quantity right here, instead of using changes, we can use the derivatives, right? The idea is the same, correct? So we can say also that impulse is equals to force, right? Delta t. But because this is the total impulse, we can say like this, the integral, right, from t initial to t final, right? This is another way how we can represent impulse, right, as the integral of this force, right? But what is that force again? Is the average force times delta t, like in this picture. Got it? Okay, perfect. Now let's go to the next concept, which is conservation of momentum. Why momentum is important? Well, momentum is important because it's conserved. The same as energy, right? Why we use energy a lot? Because it must be conserved, right? Okay, now let's see how momentum is conserved. Imagine that we have a collision of two objects, right? Two objects collide. We have this object, right, moving in this direction, or this object moving in this direction. This is m1, right? This is m2, correct? And this is initial velocity 1, right? This is initial velocity particle 2, right? Like that. Okay, now let's see, how do we define then the conservation momentum? Well, in this way, I think I need more room, right? More room. Okay, let me do it this way. Look, we have at the beginning, right, these two masses that are supposed to collide, right? And then what happens when they collide? Well, they are making contact. And then what happens after collision, right? They move away from each other. Okay, so right here they're moving away from each other, correct? And the same thing, this is M1, this is M2, this is M1, this is M2. This is initial condition, right? Initial velocity, right, particle 1, initial velocity, right, particle 2. The same thing happens right here, right? Now that right here is gonna be final, right? It's gonna be final velocity, right, particle 1, final velocity, particle 2. Perfect. Now, let's see, what is the total momentum before collision, right? And the total momentum after collision, let's do it. So right here, what do we have? M1, V1, V initial, right, 1, plus M2, right, V initial 2. And right here, what do we have? M1, V final 1, plus what? M2, V final 2. Perfect. This is before, right? Before, and this is after collision, right? After collision. Okay, now what do we have right here in the impact? Well, we have forces, we have an interaction. Look, when we're dealing with interaction, we're dealing with forces, right? And one of those cases is when we have impact, collisions, like in this case. Okay, great. Now what do we have in this case? We have the force of particle 1, right? And this is the force, right, on particle 2. According to Newton's third law, remember we have that F1 is equals to, right, negative F2. Action reaction law, remember? Okay, perfect. Now, what happens when we multiply this by time? When we multiply this quantity by time, what do we have? Well, we have that this stays the same, right? The same equals, right, remains for both sides. Perfect. But what is this? Force times time. Force times time we found before that is impulse. And impulse also equals to a change in momentum. So what is this then? That's the change in momentum, right? Particle 1 equals to negative change in momentum, particle 2. Correct? But how do we define change in momentum? Well, change in momentum is what? Is M1, right, V1 initial plus what? M2, V initial 2, right, equals to negative M1, V final 1, right, plus what? Is that correct? No, it's gonna be what? one final, right? Because only for one, I can believe it. Particle one, okay, I can believe it. Okay, initial, this is negative because it's the change, right? Is there gonna be the change? It's not plus, right? It's negative, of course. So it's equals to 1, right? Now this is gonna be particle 1, right? Particle 1 be what? To a final, right? Well, particle minus because it's a change. Okay, it's the change, right? Times v what? To initial. Perfect. Okay, much better. I was doing something. Okay, perfect. It's gonna be the change, remember, in momentum. Well, because we have this negative, so it becomes negative, right? It becomes positive. Now let's arrange it in this way. So what do we have right here? We have M1, B final 1, right? Now look, this quantity that has final velocity, right? Which is this one. So it becomes a negative because of this sign. The center of the side becomes positive, plus what? M2 V2 final, right? Equals to, look, this quantity, this term, right, is negative, becomes positive in the other side. So this becomes M1 B1 initial, correct? And this minus times minus is positive, right? Plus M2 V2 initial, right? Perfect. But what is this? Look, this quantity, this side, is just this one right here. Look, after collision. And what should be this one? This one is just this one, right? Before collision. Correct? So it's the same. So the total before collision is equal to the total after collision. So momentum is conserved. That's why momentum is important, because it is conserved. Right? Okay, perfect. Now, when we're dealing with conservation momentum, we pay attention in two special cases. When we have collisions, of course, we have a completely elastic collision and completely inelastic collision. Okay, look, these are two special cases again. We have collisions. We have two types, mainly two types, right? Or special cases, right? We have elastic collision. And we have inelastic. Collision. Okay, perfect. Now, when we have elastic collision, momentum and kinetic energy are conserved. Right here, momentum or linear momentum, right? Momentum and kinetic energy are conserved, right? Are conserved. When we're dealing with inelastic collisions, only momentum is conserved. Is conserved. Okay, now let's give some analysis on these two cases that help us to create a general equation, right, to solve problems. Okay, let's do it. When we have the, let's say this is case, because the analysis is easier, is when we have inelastic collisions. Okay, inelastic, right, collisions. This is the simplest case, right? Imagine that we have two objects. One of them is at rest, right? This initial velocity is 0, it's at rest. And this one, right, let's call this M1, right? This is M2. And this one with this initial velocity, right, in this direction. So when we are dealing with elastic collision, completely inelastic collision is when we have, right, an object, like in this case at rest, we have another one moving toward this one, and they hit and stick together and move as a single piece. Okay, this is a case for completely inelastic collision. Okay, let's do it. So what happens later? Well, we have this system, right, moving as a single piece. Imagine, again, this is M1, this is M2, and we have, right, final velocity for both. It's the same. Perfect. So how we can solve these problems again? Using conservation of momentum means what? The momentum before the impact equals to the momentum after the impact. Okay, let's do it. So what do we have before the impact? Well, we have only m1, v1, right? Initial plus 0, because velocity is 0 right here, equals to the total right after the impact, which is what? Because this form together, right, a single mass, right? So it's gonna be the total mass with the same final velocity, right? m1 plus m2 times, right, final velocity. Correct? And then from here you can solve for any quantity. You can solve for initial or for final, right? In general, this is the analysis for inelastic collisions. Now let's go to the other type, which is completely elastic collisions. Okay, let's do it. Okay, elastic collisions. Great. Now, in this case, imagine one more time, we have an object, two objects, right? Two objects moving right in opposite directions. M1, this is M2, correct? And then they collide. What happens after collision, right? They move right in opposite direction. Again, this is initial 1, right? And this is initial 2, right? Initial 2. Right here should be final. Should be right. Final 1, right? So final velocity, right? For this is final 1, correct? This is for final 2. Okay, perfect. The same masses, correct? Well, different masses, but this mass is same as right here. Okay, let me label M1 and M2. Okay, perfect. Now, as we mentioned before, when we're dealing with elastic collisions, we have that momentum and kinetic energy are conserved. Okay, so for this case, we use these two equations. We have for momentum m1 v1 initial plus what? M2 v2 initial, right? What equals to m1 v1 final, right? Plus m2 v2 final. This is momentum. What about for energy? Well, for energy we have the equation for kinetic energy. Is what? 1/2 m1 v1 initial, right, square plus what? 1/2 m2 v2 initial, right, equals to m1 this is a square, right? This is a square right here, square plus okay, 1/2 m1, right, final 1, right, square plus what? 1/2 m2, right, final, right, 2 square. Okay, so when we combine these two, right, these two equations, we create a set of equations that give us the final velocity for the impact, right, once we know the initial velocities. You can do it. Again, you can solve for one quantity right here and apply it right here, and at the end you will find these two equations, right? At the end, when we are dealing with elastic collisions, we get to these two equations. Let's do it. Okay, we have the first one. Again, this is to find the final velocities once we know the initial velocities. Okay, and this is the first equation. The final for particle 1 is equals to 2m1 over, right, m1 plus m2, right, the initial velocity of particle 1, correct, plus m2 minus m1, correct, divided by m1 plus m2 times v, the initial velocity, right, for particle 2. And the same thing, the final velocity, right, for particle 1 is equals to, it's gonna be the same, we switch them, it's gonna be m1 minus m2, right, over m1 plus m2 times v initial 1, right, plus 2m1 over m1 to m2, right, m1, correct, plus m1 plus m2 times the initial velocity, right, particle 2. So these are the equations found when we combined, right, kinetic, right, energy and momentum. Okay, and with this we can solve problems for, right, final velocities once, right, the initial velocity of the particles are provided, are given. Okay, perfect. Now finally in this section, let's go to collisions in 2D. Okay, let's do it. What happens when we are dealing with collisions in 2D? Okay, this is the simplest case. Imagine that we have an object, right, moving in this direction, this mass, right, with this initial velocity, and we have another object right here, right, m2, which is at rest, right, velocity equals to 0. What happens when they collide? Well, when they collide, it's found that later, right, let's say m1 goes in this direction, right, and m2, right, goes in that direction. Correct, this is m2, and this is the final velocity, right, for particle 1, and this is the final velocity for particle 2. Imagine, right, imagine that this is the angle for 1, right, this is theta of phi, right, and it's gonna be what, theta. Imagine. Okay, how do we solve this problem again? Conservation of momentum. But now this is in 2D. So means what? We need to find the conservation of linear momentum in the x direction and the conservation of linear momentum in the y direction, and then we combine them. Right? Okay, let's do it. So let's label this as the x direction and that as the y direction. Okay, now let's find the term momentum, right, in the x direction. And what do we have in the x direction at the beginning? Well, at the beginning we have that only, this is before collision, right? This is after collision. So before collision, we have only this object moving, and this is 0. So momentum for this one is 0 because it's not moving. Perfect. So we have only m1, right? The initial, right, velocity for particle 1 is equals to, right, the final, right, component, which is what? m1, right, v1 final cosine theta. Remember, it's component in the x direction, component in the y direction, correct? So it's gonna be cosine, and that one in the y is gonna be sine, correct? Plus what? Plus m2, right? Final velocity, particle 2, right? Cosine, well, this is cosine phi, right? Plus cosine phi is cosine theta, correct? This is in the x direction. What about in the y direction? Well, the same thing, right? Equals to, what is the total? Well, at the beginning, we have only x component right here, so y is 0. Right here is velocity is 0, so momentum is 0, x and y. So what do we have at the beginning then? 0 equals to what? Well, now we have this component goes down, goes up, right, for this m1, and for m2, right, component goes down. Okay, perfect. So what do we have then? It's gonna be m1 times the final velocity of particle 1, right? Let's take this to be positive, right, sine phi, right, minus because goes down, right, m2 v, right, to final, times what? Times sine, right, theta, correct? And now we can combine these two equations to solve for the quantity we are looking for, correct? We can look for initial velocity, we can look for the angles, right, and so on. Also, if this collision is elastic, right, we can use, or it depends on the problem, right, we can use conservation of energy because it's elastic. Remember, when we have elastic collisions, energy, momentum are conserved. Okay, for momentum, in any case, is conserved, right? Could be inelastic or inelastic. But look, this is the idea. When we're dealing with collision and momentum, we say that momentum is conserved, but it's conserved just before and after the collisions, right? We have a particle right here. We don't know what is happening right here, but just before and just after the impact, momentum is conserved. After that, we don't know what happens. Before that, we don't know what is happening. But just before and after the collision, right, momentum and elastic collision energy, right, could be conserved. But in general, momentum is conserved just before and just after the collisions. Perfect. Now imagine again that we have a completely elastic collision, so we can use also the conservation of energy, which is what? 1/2 m1, right? Initial velocity particle 1, right? The square must equals 2 to what? 1/2 m1 final, right? Particle 1 square plus 1/2, correct? m2, right? Final velocity, right? 2 square. So we can use it. We can use another way. So when we can use one or the other one depends, right? If we have one unknown, right, in the problem when we have collisions, we can use, is completely elastic, we can use energy, which is this is one, or we can use conservation of energy, right? If we have two unknowns, right, in the problem, usually we have to combine them, right? Momentum and kinetic energy when we have two unknowns. Again, when we have one unknown quantity, usually we use momentum, right? Only one equation, one concept, right? Or depends, right? We can use conservation of energy. Two unknowns, two equations. These two